Hello, in this video we're going to go over Gram-Schmidt Orthogonalization Process. This process is used to obtain orthogonal bases relative to a given inner product. So here is the process. I will explain how this works and then we'll do an example. We'll prove this and then we'll do an example. So let's say you want to create vectors that are orthogonal given two vectors. Let's say you have a vector v1 and you have a vector v2 and you want to create two vectors that are orthogonal. So we discussed how we can do that earlier with two vectors. So what we do is we're going to project one of these vectors onto the other. So as we talked about this would be inner product of v1, v2 and v1 divided by length of v1 squared times v1. This is that vector. And if we subtract it from v2, we get v2 minus this. So this vector is the projection of v2 onto v1. If we subtract the projection from v2, we get this vector divided by norm of v1 squared, length of v1 squared times v1. And when we do that, we will obtain something that is orthogonal. And when we were doing the Cauchy-Schwarz inequality, we saw that this is in fact orthogonal to v1. And clearly they also span the same set. It's not very difficult to see, but at least intuitively it's clear that this guy and v1 span the same space as v1 and v2. If you repeat the same process, you will obtain a set of vectors that is orthogonal. So here is now the statement of the Gram-Schmidt process, and then we will go over the proof, and then we will in fact solve do an example. Let angle bracket comma angle bracket be an inner product on Rn, and let v1 through vm be linearly independent vectors in Rn. Define vectors w1 through wm recursively as follows. So the first vector would be just v1. The second vector would be the second vector minus projection of the second vector onto the first vector, onto w1. Then we take v3 and then we subtract the projection of v3 onto the previous w's, w1 and w2. Keep in mind that you'll have to do that onto w's and not v's. When we subtract those projections, we will obtain things that are orthogonal. And not only that, but it would also be an orthogonal basis for the subspace of Rn spanned by v1 through vm. Okay, so we are going to actually go over the proof of this one. So the proof is by induction. On M, we will prove the claim. Okay, so for m equals 1, if you have w1 equals v1, this is clearly orthogonal basis, an orthogonal basis for the span of v1 because it's just the same vector. So that's pretty straightforward. So this is our basis step. Now let's assume that w1 all the way to wm minus 1 are orthogonal, or I guess form an orthogonal basis for the span of v1 through vm minus 1. So what we're going to do is we're going to show that wm is orthogonal to the previous ones, which would mean they would be orthogonal, and then we will also show that they would span the same space. So if you look at wm by definition it is vm minus projection of each one of the projection of vm onto each one of the previous vectors. So v1 w1 divided by w1, which is just length of w1 squared times w1, etc. minus vm Wm minus 1 divided by length of Wm minus 1 inner product multiplied by Wm minus 1. We're going to take Wm and do the dot product of this one, inner product of this one, with one of the Wj's. So let J be between 1 and m minus 1. So we will do Wm inner product with Wj. So this is, I'm going to use linearity, Vm Wj minus, now Wj is orthogonal to W1, Wj, W2, all the way to Wj minus 1. The only one that is not orthogonal to is Wj. So it would be Vm Wj over Wj, 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 and Wj. And these two cancel. These two are the exact same thing. So the difference would be 0. So what that means is that W1 through Wm are orthogonal. Now, if I also show that they form the same space, their spans are the same, then we are done. So what we know is that the span of W1 through Wm minus 1 is the same as the span of W1 V1 through Vm minus 1. We know this one. Now, if you look at the last one, Wm is Vm minus a bunch of linear combinations. It's Vm Wj over Wj, and then times Wj. J goes from 1 to m minus 1. Now, since each of these is in the span of V1 through Vm minus 1, this would be in the span of V1 through Vm. So in other words, Wm is in the span of V1 through Vm. Similarly, Vm is also in the span of W1 through Wm. So because if you evaluate Vm from here, you get Wm plus this sum. Vm, and these are just scalars. This is in the span of W1 through Wm. So what that means is, if you look at these two spaces, span of V1 through Vm and span of W's, okay, we know that each of these is in this one, and V sub m is also in the right side. Each of these is in this one, and this one is also in the left side. So therefore they must be the same. This is by one of the examples in the notes, that if S is a subset of span of T and T is a subset of span of S, then the spans must be the same. Span of S and span of T must be the same thing. So this shows that W1 through Wm must be a basis for orthogonal bases for a span of V1 through Vm. Now, sometimes you might start from a set of vectors V1 through Vm that are not a basis. They may not be linearly independent. And by the way, the reason that they form a basis is that they are generating, and we know that dimension is m because we know these are linearly independent. Because they are generating and the dimension is m, they would have to be linearly independent. Now, if you start from a set that is not linearly independent, you're still going to end up with an orthogonal set, but some of them are going to be non-zero. Those that are 0 should be dropped The rest of them that are non-zero would be a basis. Okay, so this means every subspace of Rn has an orthogonal basis with respect to any arbitrary inner product. Because what we know is every subspace has a basis, then the Gram-Schmidt process tells us we can turn that basis into an orthogonal basis. We say vectors v1 through vn are orthonormal relative to an inner product if they are orthogonal and the inner product of each one of them with itself is 1. Okay, so let's do an example on the Gram-Schmidt process, and then we will talk about perpendicular complement of a orthogonal complement of a subspace. Find an orthogonal basis for the subspace of R4 generated by these. So the first thing that I'm going to do is I'm going to actually show that these three vectors are linearly independent because the Gram-Schmidt process requires them to be linearly independent. If they were not, you would end up with a bunch of zeros which you could eliminate. But that's not very difficult. If you look at 1, 2, 0, negative 1, 0, 1, 0, 2, and 0, 0, 2, 1, this is in echelon form with 3 pivot entries, and these are the pivot entries. This one, and this one are pivot entries. That means the 3 vectors given are linearly independent. Okay, so now I can go ahead and find an orthogonal basis. They didn't tell us what specific inner product we should use, so since it was not given, we will use the standard dot product. So W1 is just the first vector, 1, 2, 0, negative 1. W2 would be the second vector, which is 0, 1, 0, 2, minus the inner product of the second vector, 0, 1, 0, 2. It would be the projection onto the first vector, 1, 2, 0, negative 1, and then times 1, 2, 0, negative 1, and then we'll have to divide by the length of this vector squared, which is the inner product of this with itself. This would be 0, 1, 0, 2. The dot product of these two would be 0 plus 2 plus 0 minus 2, so that's just 0. So we can just ignore that portion. W3 would be V3, the third vector, which is 0, 0, 2, 1, minus the projection of this vector onto the previous two vectors, previous W's. So the first one is 1, 2, 0, negative 1, divided by 1, 2, 0, negative 1. And by the way, this was negative 1. I had a typo there, but it didn't really matter at the end. Times, I'll have to multiply that by 1, 2, 0, negative 1, and then subtract projection of this, which is 0, 0, 2, 1, onto the second vector, 0, 1, 0, 2, divided by length of this vector squared, 0, 1, 0, 2, multiplied by 0, 1, 0, 2. And after calculation, we get the final answer. So we get 0, I'm going to write it down, 2, 1 minus, okay. So the dot product of these two, the first one is 0, the second one is 0, 2 times 0, that's also 0, so that's minus 1, divided by 1 plus 4 plus 1, that's 6, times 1, 2, 0, negative 1, and then minus 0, 0, 0, 2 over 1 plus 4, which is 5, multiplied by 0, 1, 0, 2, and this would be 0, 0, 2, 1, plus 1 over 6, 1 over 3, 0, negative 1 over 6, and then minus 0, 2/5, 0, 4/5. And this would give us the last vector. So these three vectors form a basis for the span of the three vectors that they gave us. Okay, so next topic we're going to talk about is orthogonal complement. Given a subspace W, the orthogonal complement of W relative to an inner product is denoted by W perp, and it's defined by all of the vectors that are orthogonal to vectors of W. What does that mean? It means all of the vectors in Rn that the inner product of V and W is 0 for all W in W. So it is not very difficult to see that this is in fact a subspace, and that's the subject of our next discussion. But before I do that, let me look at like one example. So for example, in R3, if W is a vector, is a line through the origin, then W perp is all of the vectors through the origin that are orthogonal to W. That would give you a plane. If your W is a plane, so let's say W is a plane through the origin, then all of the vectors orthogonal to that would give you a line. So this would be W perp. So you kind of see the relation here. If you are working in R4 and W is a plane, W is a two-dimensional plane, then W perp would be two-dimensional. It would be two-dimensional because you have two more dimensions left. In fact, that's the subject of our next theorem. So let W be a subspace of Rn, then W perp is a subspace of Rn, and the sum of the dimensions is exactly n. So let's prove this. First, we want to show that W perp is a subspace, so we will have to use the subspace criterion. So we will use the subspace criterion. So first I'm going to have to show that 0 is in W perp. So let W be a vector in W. Then 0 inner product with W is equal to, I can write down 0 as 0 times 0. And then I can use linearity and take it out. So that just gives me 0. So this means 0 inner product with W is 0 for all W. What does that mean? It means 0 is in W perp because the inner product of 0 and everything in W is 0, therefore 0 is in W. So that shows the first condition. Now suppose W, maybe something else, maybe X and Y are in W perp and C is a scalar. We will have to show that X plus Y is also in W perp. So what we know is that for, so by definition of W perp, the inner product of X and W and Y and W are both 0 for all vectors W in W. Now if you look at X plus Y, inner product of that with W, that would give you the inner product of X and W plus the inner product of Y and W, and of course both of these are 0, so this would be 0. If you look at Cx and W, this would give me by linearity C times XW, which would be C times 0, which is also 0. So these two tell us that X plus Y and Cx are both in W. And this is of course for all W. These two are of course for all W in W. So these are in W perp, I mean. So therefore W perp is in fact a subspace. Okay, so now we will have to show that the dimensions add up to n. So suppose, so choose a choose a basis for W and choose a basis for W perp. So suppose W1 all the way to WK is an orthogonal basis for W, and let's say WK plus 1 all the way to WM is an orthogonal basis for W perp. Okay, so first thing I'm going to show is that W1 through WM are in fact linearly independent. And the reason is that if you look at the inner product of Wj and Wk, so if j is less than or equal to k and greater than or equal to 1, and L is greater than k less than or equal to m, then inner product of Wj and WL is just 0. So let me do this a little bit. So this is 0. This is because WL is in W perp. So WL is orthogonal to everything in W, and WJ is in W. So WL is orthogonal to everything in W, therefore the inner product of WJ and WL is in fact 0. So now, what does this mean? This tells us that the vectors W1 through WM, they are orthogonal. Okay, so this both of these are all orthogonal because W1 through WK are orthogonal, and WK plus 1 through WM are also orthogonal, and they're also orthogonal. We showed that they are also orthogonal to each other. So this is an orthogonal set. So that means they are linearly independent by a theorem. They are linearly independent, and notice that none of them are 0 because they were part of a basis. Okay, so now what we have to show is that we will have to show that a span of W1 through WM is in fact Rn. If we show this one, then they are linearly independent. They are also spanning, therefore M would have to be the same as the dimension of Rn, which means M must be n, and then we're done. Okay, so we have to show this is the same as that. So let's assume that we know that span is inside Rn, so assume X is in Rn. We will have to show in fact X is in fact a linear combination of W1 through WM. Okay, so what we're going to do is we're going to look at the value of X minus the projection onto W1 through WM. So what does that mean? So consider this vector. I'm going to use basically the idea of Gram-Schmidt. Consider X minus projection of X onto Wj J goes from 1 to I believe it was k. Let me just make sure. Yeah, k. So consider this vector. Let's call that y. If you look at this vector, the inner product of this vector y and xj is going to be, so it is inner product of x and xj minus, so this is for j between 1 and k, minus, so all of the inner products are 0 because wj's are orthogonal to each other, except for one of them, except for x wj over wj times wj, which means this is exactly 0. So what we just showed is that if you take the dot product of and this is wj. Y and wj, you just get 0. So what does that mean? Thus, y wj is 0 for j equals 1 through k. Now, if you take the linear combination, if you take y, inner product with sum of cj wj, j equals 1 to k, this is 0 bilinearity. But every vector in W is in this form. So that tells us V is in fact in W perp. I'm sorry, Y is in fact in W perp, because this can be any vector in W. We know that vectors in W are linear combinations of wj's. So this tells us that Y is in fact a linear combination, let's say dj wj, j equals k plus 1 to m. So now I have this. I have x minus sum of x and wj over wj times wj equals sum of dj wj. This one is j equals k plus 1 to m. This one is j equals 1 to m. So if you move this guy to the other side, you will get x is in the span of w1 through wm. So what did we show so far? We showed that span of w1 through wm is in fact the same as Rn, because we know every element of Rn is in the span. We just showed that. And of course, every element of the span is inside Rn. So these two are the same. But since W1 through Wm, they are linearly independent, they form a basis. They form a basis for Rn. So that tells us m is exactly the dimension of Rn. And what is the dimension of Rn? That's n. So therefore, m and n are the same. But if you go back, m was k plus m minus k. K was the dimension of w. M minus k was the dimension of w perp. And that's exactly n. And that completes the proof. Let me show you when we made those assumptions. I took a set that was an orthogonal basis for w. So what does that mean? It means k is the dimension of w. And then I took a set that was an orthogonal basis for w perp. So it means m minus k is the dimension of w perp. So in order to prove that the dimension of w and w perp add up to n, I will have to show m is equal to n. And that's exactly what we did in this process. So this really uses the idea of the Gram-Schmidt process, which really heavily lies on the fact that if you take a vector, subtract projections onto orthogonal vectors, you get another new orthogonal vector. And this brings me to the end of this video. So next time we'll talk about norms and how they're going to help us understand geometry, and we'll do some more examples on norms. And I will see you in the next video.